Assalamualaikum. We will be looking at the bipolar junction transistor BJT single stage amplifier so that we can carry on with our first topic, multi-stage amplifiers in ELE 426. Before we can do multi-stage, we need to have a good grasp over the single stage, because we will be doing the analysis of the single stage again and again in between all our analysis. So we will be looking at BJT, and we know that BJT there is NPN and PNP transistors. What we will be looking at in this video is NPN. The symbol, there are three terminals: collector, base, and emitter. Okay. There is DC and there is AC analysis. So if we are doing our DC analysis, okay, so when we do DC analysis, we will be relating the collector current, emitter current, and the base current. Okay, take note that all these arrows, okay, the arrow of IC going into the terminal collector and base current going to the base and emitter leaving the emitter, okay, is a standard notation that we follow. So IE is equals to IB plus IC, and that we can relate IC to IB, collector current, to base current by the common emitter gain amplification factor, beta. Okay, and beta is usually large, maybe bigger than 50 up to 200, say, and you can relate the emitter current to the base current using these two equations above to become beta plus 1 IB. And if you look at this, IB is usually very small. IB is around microamp. IE and IC is usually around milliamp region. And if I want to relate IE to IC, IE is equals to alpha IC, where alpha is the common base multiplication factor, and alpha is very close to 1, and beta is usually bigger than 50, less than 200 maybe, okay, from BJT. That's DC analysis. Now let's look at AC analysis. But before we go into AC analysis, let's have a look at the BJT single stage amplifier, so that we have a sense of where this AC analysis comes from. Okay, if you look at this circuit in front of you, there is this BJT, and this bipolar junction transistor is biased by R1, R2, RC, RE, and the power supply of VCC and negative VCC or ground. You can have different resistive networks to bias the BJT. This one that I'm showing you here is the voltage divider biasing circuit, and if the BJT is biased in the active operation, which means that the base emitter junction is forward biased and the collector base junction is reverse biased, this amplifier can now amplify an input signal so that it becomes bigger, okay? And the base emitter junction here can be approximated to 0.7 volts. So when you do your analysis for DC biasing, what you are analyzing is actually what IC, IB or IE is now, or VBE or VCE. But when you do AC analysis, you're actually analyzing how the input signal here is amplified to become an output signal that is larger. When we want to do AC analysis, what we need from the previous example is that we need to find out what the DC current IE is, because in our AC analysis, what we are going to do is that we will be replacing our BJT. It will be replaced by a small signal equivalent circuit, where this is your base, this is the emitter, and between the emitter and collector there is a dependent current source and there is an output resistance. So this dependent current source, the current is beta IB, where IB is the current that flows from the base to emitter, flowing through this small signal AC resistance beta RE. Okay, and this is our output resistance R out. So all of this, base, collector and emitter, is what you call the RE model, which we will use to replace or to represent BJT. When we know emitter current from here, we will be applying the RE model parameter, small signal RE, which is equals to 26 millivolts over IE. 26 millivolts being the thermal voltage and IE being the biased current at the emitter terminal of the BJT due to the DC biasing circuit. Before I continue into the AC analysis, I'd like to point out here that RE, the small signal RE, is not the same as the emitter resistance RE in the DC biasing circuit here. When we want to analyze the BJT amplifier, we will first do the DC analysis. Okay, when we do the DC analysis, the capacitors, I did not label the name of the capacitors here. So let's say this is C1, this is C2. This input and output capacitances C1 and C2, it will be an open circuit because in DC analysis, all capacitors become open circuit, and so does CE. Okay, but when we do AC analysis, C1, C2 and CE becomes short circuit, and CE bypasses RE because it creates a path of short circuit that makes the emitter current to not go through RE, and so RE is effectively non-existent because it's been bypassed by CE in AC analysis. So for us to do our analysis of this amplifier, first we need to do the DC analysis and then we do the AC analysis. So let's have a look at how we do the DC analysis. When I want to do DC analysis, I will redraw the circuit and all these capacitances become open circuit. This one becomes ground or negative VCC. Okay, I do not have the capacitances anymore. In AC analysis, when I redraw the circuit, all DC sources becomes AC ground and all capacitance becomes short circuit. So if I redraw my earlier amplifier, it will look like this. Still have R1, R2, RC, but RE is bypassed, so it's effectively not there for my AC analysis. Ground is ground, and any DC sources also becomes ground. Vin, okay? And if I were to draw, depends on the textbook that you're using. The textbook that is covered in semester 1 and diploma courses so far has always been Ballstadt, and they use the small signal equivalent circuit. If I were to draw the circuit, it will look like this. R1 and R2 will be effectively in parallel, because if you see, R1 is here connected to ground and R2 is also paired up in one terminal and connected to ground. So ground and ground is connected. I have R1 and R2 in parallel. I'm going to label this base, collector and emitter. So this is my base, emitter and collector. At the base, I will have a resistor, which is beta RE, which is my small signal model. And between emitter and collector is the beta IB, and I have my output resistance AC. And between collector and ground, I can see RC. So this is V out, okay, and this is V in. Here I have beta IB. This small IB is also not the big IB in AC analysis. Okay. Word of caution: IB is not the same as IB of DC current. Okay. The voltage gain is V out over V in. So we will be finding an expression for V out, which is at the output terminal here, that consists of the term IB. And then we will also have V in here to go into here, which also has the term IB. So IB, even though we write it down, it leaves just to get itself cancelled. Okay, now let's have a look at the example.